In section 7.2, we're going to talk about linear functions and their graphs. So back in 7.1, we introduced the idea of equations in two variables and then functions. So in this section, we're going to talk about a very specific type of equation in two variables, linear equations in two variables. Now, this is not to be confused with what we talked about in sections 6.2 and 6.3, where we were talking about linear equations in one variable. This is going to be a little bit different, okay? So what we have here to start out with is a linear equation in two variables is any equation of the form ax plus by equals c. Okay, and we have some conditions. The conditions are that a, b, and c are real numbers. That means a, b, and c, the coefficients of x and y, and then the constant. Those can be fractions, they can be decimals, they can be positive, they can be negative, they can be integers, whole numbers, whatever. Okay, we just have this condition that a and b cannot both be zero at the same time. We will talk later in this section about what happens if A is zero and what happens if B is zero, but just know they both cannot be zero at the same time. One can be zero, but then the other one can't. Okay? Now, what I want to remind you of is when we're talking about linear, so when we're talking about these equations, whether in one variable or two variables, linear means exponents of one on the variables. Okay, so that's what we mean by linear. And notice here when we look at this format, ax plus by equals c, x and y have coefficient, or not coefficients, they have exponents of 1. Okay, so again, a linear equation in two variables is any equation of the form ax plus by equals c, where a, b, and c, that's the coefficients on x and y, and then the constant, those have to be real numbers, fractions, decimals, positive, negative, whole numbers, whatever. We just have the condition that a and b can't be zero at the same time. Okay? Now, a few other pieces of information about this. We do call this ax plus by equals c standard form. Okay, we will talk about different forms of linear equations in two variables. We'll talk about slope-intercept form, point-slope form, horizontal lines, vertical lines. But this right here, this just ax plus by equals c, that is what we call standard form. Okay. Now, what we need to understand about these equations as far as their solutions are concerned, we have two really important bits of information here. First, there are infinitely many ordered pair solutions to a linear equation in two variables. And that shouldn't come as like a huge surprise to you because in section 7.1, we acknowledge that solutions to equations in two variables were ordered pairs. Very specifically, ordered pairs that build the graph of that equation. Okay, so the same is going to be true about a line. If we are graphing whatever this equation is, we have all of these little points that make up the line. And each one of those points is an ordered pair. And because this line goes on forever, okay, we have infinitely many ordered pair solutions, okay? And just keep in mind the ordered pairs in the solution set are the points on the line of the graph. That's really important that you understand that. It's not just arbitrary ordered pairs that we're saying are the solution set. We're saying that if we plot all of these ordered pairs that create the solution set to a linear equation in two variables, we are quite literally building the line for that equation, okay? Now, we know how to graph by point plotting, okay? So graph by point plotting, we talked about that back in the previous section. So graph by point plotting, you can go back to section 7.1. We talk about point plotting there. You can certainly graph lines by point plotting, but because lines are going to have some special qualities, they're going to have a few easier ways to graph them. Okay, so point plotting always works. It's a little bit more tedious when it comes to lines. There are definitely quicker ways to graph a line. So we're going to start by looking at a really important feature of linear equations in two variables. What we're going to talk about now, well, it's intercepts. You can see that from the title here. Intercepts apply to really any equation, but in a linear equation, we can use intercepts to graph. You can't always use intercepts depending on the type of graph, but for a line, you certainly can. Okay, so let's talk about intercepts. What in the world is an intercept? Okay, so generally speaking, intercepts are points where graphs cross the x or y axis. And this is true for any kind of graph. Doesn't matter what the shape is, doesn't matter the style of the graph. Just know that if a graph, any shape, touches the x or y axis, that point where it touches or crosses would be an x or a y intercept, okay? So intercepts are points where a graph crosses or touches the x or y axis, okay? So a point where a graph crosses the x-axis is called an x-intercept, and it is always going to be of the form, like ordered pair form, x comma 0. And I'll explain why in just a second, okay? And then a point where a graph crosses the y-axis is called a y-intercept, okay? And it is always going to be in the form, as far as ordered pairs are concerned, it's always going to have an ordered pair of the form 0 comma some y value, okay? So in the first example here, it says we're going to learn to identify intercepts from a graph, table of values, and equations. And the first example we have here, it says identify and label all intercepts. We're going to first look at a graph, and this is really, really important, okay? So going kind of back to that stuff we talked about in section 7.1, we know that this is the x-axis. And we know that this vertical number line that creates this Cartesian plane, this is the y-axis. So you kind of have to go back to the definition of the Cartesian plane. It is this two-dimensional space where we can graph equations in two variables. And it is created by two number lines, a horizontal number line and a vertical number line that intersect, forming right angles. Well, the vertical number line is your y-axis and the horizontal number line is your x-axis. And if you look at this red line that is graphed, you can see this red line crosses the y-axis and the x-axis. That means this line has two intercepts, okay? I will tell you that lines have at most two intercepts, okay? Now, other types of graphs could cross an x or a y-axis more than once, but for lines, at most once, okay? So let's look at this y-axis, okay? The line, the red line, does cross the y-axis. That means we do have a y-intercept. And if you'll notice, to get to this ordered pair from the origin, I would not go left, I would not go right. So that tells me that the y-coordinate is 0, and that is always going to be the case for a y-intercept. To live on the y-axis, your y-coordinate is going to be some positive or negative value, but your x-coordinate has to be 0, okay? And then from the origin, if I don't go left or right, I just go up or down. In this case, I go up 1, 2, 3, 4, 5. So this y-intercept would be the ordered pair 0, 5. All y-intercepts are going to be of the form 0, comma, some positive or negative y value, okay? Now, to live on the x-axis, from the origin, I would definitely have to go left or right, but then to stay on the x-axis, I would never go up or down. So let's look at this x-intercept that we have over here. So this point right here is an x-intercept. Okay, to get to that ordered pair from the origin, I would go to the right 1, 2, 3, and then I wouldn't go up or down. That's how I can live on the x-axis. I go left or right, but then I don't go up or down. So your x-intercepts are always going to have an ordered pair with some positive or negative y-coordinate first, in this case, positive 3. And then the y-coordinate has to be 0, okay? So you can always spot intercepts because one of the coordinates of the ordered pair is going to be a 0. So for intercepts, one of the coordinates from the ordered pair must be 0. If you have coordinates that are not 0, you're a perfectly lovely point in the Cartesian plane. You're just not an intercept, okay? So intercepts are just special types of ordered pairs that live specifically on the x or y axis, okay? So we've figured out or identified intercepts for a line based on a graph. Now let's look at a table, okay? Now this doesn't necessarily represent a line here, but let's figure out our x and our y intercepts, okay? Now remember, I just told you up here that intercepts, okay, when you're dealing with intercepts, one of the two ordered pairs, not one of the two coordinates in the ordered pair must be a 0. So that's what we want to do. We want to go and find the ordered pairs from this table that have zeros. And just as a quick reminder, when you have a table of values, that's definitely a table of values here. When you have a table of values, the first column is your x coordinates and the second column is your y coordinates, and you can combine those to be ordered pair solutions to some graph, okay? Now, again, this one is not necessarily a line. I'd have to double check it and plot it, but all the same, we can still find intercepts, okay? So our first ordered pair is -5, -6. Neither coordinate is 0. This is not an intercept. Next, we have -2, comma, -4.8. Again, neither of those coordinates is 0. We're not an intercept. And then if we look at the fourth ordered pair, we have 5, comma, -2. Neither of those coordinates is 0, so none of these are intercepts, okay? None of those are intercepts. However, if we look here at the third point in the table, we have the ordered pair 0, -4. Okay, so if I were to plot that, At the origin, I would not go left or right, but I would go down 1, 2, 3, 4. So this is the ordered pair 0, -4. It is clearly on the y-axis. That would make this a y-intercept. Okay. And then the last point in this table of values, we have the ordered pair 10, 0. So if I were to plot this, 6, 7, 8, 9, 10. From the origin, I would go to the right 10, and then I would not go up or down because that y-coordinate is 0. So you can see right here, this is the ordered pair, 10, 0, very obviously lives on the x-axis. That would make this an x-intercept. Okay, so it's pretty easy to spot your intercepts from a graph or from a table of values. Okay, so be prepared to do both. Look at a graph and determine what ordered pairs are. Look at a table of values and not ordered pairs. Look at a graph and determine what intercepts are, and then look at a table of values and determine whether or not you have intercepts listed. Okay, now what's a little teeny, and I mean teeny tiny bit more difficult, is when you have just an equation. If you have a table of values or you have a graph, it's pretty easy to spot those intercepts. You're just looking for points on the x or y axis, or you're looking for ordered pairs that have a 0 coordinate somewhere. When you're looking at an equation, you have to do a little more work, okay? This is not difficult. You just have to do a little bit more work. All right, so for example 2, we're going to identify and label all intercepts, but notice for part A and B, we have equations, okay? So steps to find intercepts from an equation. The first thing we want to do is we're going to kind of determine, are we going to find our x-intercept first or our y-intercept first? I generally go x-intercept first, okay? So to find the x-intercept, we need to let y equal 0 and solve for x. Why in the world would we do that? Well, if we are looking at intercepts, okay, and let's say we have some arbitrary line, okay? Well, let's do blue, okay? Well, this graph crosses the x and the y-axis, and it crosses the y-axis at some ordered pair 0, comma y, and then it crosses the x-axis at some ordered pair x, comma 0. So to find an x-intercept, we have to let y equal 0, and then we can solve for x. Now, on the flip side, if we're trying to find the y-intercept, look at our y-intercepts. Well, y-intercepts always have an x-coordinate of 0. So to algebraically find a y-intercept, we let x equal 0, and then we solve for y. And something that is really, really important, if you're taking these notes on something I've printed or you're doing these notes by hand, just make sure you somehow make this really clear. Ordered pairs for intercepts are two distinct ordered pairs. You would never take an x-coordinate and a y-coordinate from an ordered pair and write them as one point. You're no longer an intercept at that point, okay? So you've got to have your x-coordinate and your y-coordinate in a single ordered pair for the x-intercept, and your x-coordinate and your y-coordinate as a single ordered pair for your y-intercept. And I'll show you in just a minute what that looks like. All right, so let's go ahead and do this. So we have the equation 3x plus 5y equals 15. I'm going to start with my x-intercept. So remember, for the x-intercept, we let y equal 0 and solve for x. So I take 3x plus 5y, but we're going to let y equal 0. So I'm just taking that the original regular equations, what I'm trying to say, and I replace y with 0. Okay, so we're basically evaluating this equation when y equals 0. We're going to figure out what x has to be. So we get 3x plus 5 times 0, which is just 0. That equals 15. Well, 3x plus 0 is just 3x. So we get 3x equals 15. This is something pretty easy that we can solve for. We want to undo the multiplication of 3 and x, so I would divide both sides by 3. 3 divided by 3 is 1, leaving me with just an x, and then 15 divided by 3 is 5. So I would say my x-intercept is 5, but as an ordered pair, I would write it as 5, comma, remember, we let y equal 0, so 5, comma, 0. Okay? Now, for a y-intercept, we let x equal 0 and solve for y. So you're always letting the opposite variable be 0. So I'm going to take that same equation, I'm going to rewrite it, but anywhere I see an x, I'm going to replace it with a 0. So I would get 3 times 0 plus 5y equals 15. Well, 3 times 0 is just 0. And 0 plus 5y is just 5y. So we get 5y equals 15. We want to undo the multiplication of 5 and y. So we divide both sides by 5. 5 divided by 5 is 1. 1 times y is y, and 15 divided by 5 is 3. Okay, so we would say our y-intercept is 3, but as an ordered pair, we want to write it as, well, we said x had to be 0, so 0, comma 3. So you have a distinct x and y intercept, and each intercept has a distinct x and y coordinate, and one of those coordinates must be 0. Okay, so you would never write this as the ordered pair 5, 0. You're going to have 5, or not 5, 0. You would never write this as the ordered pair 5, comma 3. You're going to have 5, 0 as an ordered pair, and then separately 0, 3 as an ordered pair. Okay, let's look at example 2, part B. So we have 7x minus 9y equals 0. This one is a little bit tricky, so pay close attention. For the x-intercept, remember, we let y equal 0 and then solve for x. So I'm going to rewrite, solve for x. I'm going to rewrite the equation. Anywhere I see a y, I'm going to replace it with a 0. So I get 7x minus 9y, but y is 0. Well, 9 times 0 is just 0. So I get 7x minus 0 equals 0. Well, 7x minus 0 is just 7x. And then I need to undo the multiplication of 7 and x. So I divide both sides by 7. 7 divided by 7 on the left is just 1. 1 times x is x. And then 0 divided by 7 is 0. So I would say my x-intercept is 0. So as an ordered pair, if x is 0 and y is 0, I just get the origin. Okay, so let's look and see what happens with our y-intercept. So remember, for a y-intercept, we let x equal 0 and solve for y. Remember, whatever intercept you're looking for, you always let the opposite variable equal 0. So we're going to rewrite this equation. Anywhere we see an x, we're going to replace it with a 0. So we get 7x, but remember, x is 0, minus 9y equals 0. 7 times 0 is 0. 0 minus 9y is negative 9y. So negative 9y equals 0. We want to undo the multiplication of negative 9 and y. So we divide. Negative 9 divided by itself is 1. 1 times y is y. And 0 divided by negative 9 is 0. So we already said x had to be 0. We found that y was 0. And again, we get the origin. So in this case, there is a single intercept because the intercepts match. There is a single intercept for this line, and it is the origin. So what does this really mean for us? This means this equation goes through the origin. All right. And that will happen from time to time. So hopefully we'll see another example of a line that goes through the origin. But just know, if you get the intercepts, the x and the y intercept are both the origin, the line just has to go through the origin. Okay? So that is intercepts. This was kind of a longer video because we had to describe what is a linear equation, not just describe it, but define it. We had to talk about what intercepts are. And we were able to find intercepts from a graph, a table of values, and of course, equations. Okay, so in the next video, we will talk about how we can actually use intercepts to graph a line, very specifically a line.